Hello everyone and welcome to Aquaclimb Enviro Solutions. We'll present a 4-part series on the topic environment and floods. This is third series of 4-part series and we'll explore some of the aspects of flood forecasting. We'll talk about objectives, hydrologic cycle, causes and types of floods, data analysis, modeling and forecasting, coordination and participatory approach, and some concluding remarks. A prudent person foresees danger and takes precautions. The simpleton goes blindly on and suffers the consequences. Forecasting integrates a broad range of knowledge including physics, mathematics, engineering, geography, economics, and sociological considerations, among others. The objective of this presentation is to provide key basic information on the subject flood forecasting. The presentation gives an overview of forecasting methods while avoiding theoretical treatment of complex flood forecasting tools such as hydrologic models. We'll focus on the past, the present, and the future of flood forecasting. We shall look at a broad view of future trends, including climate change, the use of drones, and community participation in flood forecasting. We all are aware of hydrologic cycle. Water circulates in the hydrosphere through a variety of complex paths to form the hydrologic cycle. The global hydrologic cycle can be divided into three components: the atmospheric water system containing the process of precipitation, evaporation, interception, and transportation. The other component in the surface water system comprising overland flow, surface runoff, and runoff into streams, lakes, and the ocean. The third component is the subsurface water system consisting of infiltration and groundwater flow. A good understanding and the quantification of these three components is critical in building an effective flood forecasting system. What is flood? Flood is typically an overflow or inundation of water from a river or other body of water which causes or threatens loss of life and property and environmental damage. It is normally overflow of water onto normally dry land. Normally the inundation of typically dry area caused by rising water in an existing waterway such as river, stream, sea storm surges, or drainage ditch. Many types of flooding are characterized by overbank flooding of the waterway. However, a flash flood, on the other hand, are caused by heavy or excessive rainfall in a short period of time, generally less than 6 hours, and are usually characterized by raging torrents after heavy rains that rip through riverbeds, urban streets, or mountain canyons, sweeping everything before them. They can occur within minutes or a few hours of excessive rainfall. Sometimes a flood event does not necessarily imply that a river has burst its banks or caused damage, but denotes an event that exceeds a defined threshold level. A flood event is characterized by the peak flow rate, time of peak flow, flood elevation, volume, duration, and timing. These parameters can be inferred from a flood hydrograph, which is the time distribution of flow, and are important when providing flood forecasts. Typical causes of flooding are heavy rains, can be caused by frontal systems, monsoon systems, convective processes, orographic lifting, snowmelt, especially rapid snowmelt caused by rapidly rising temperatures, ice jam, especially during winter, mild spells, and spring thaw, dam failure, coastal storm surges and tsunamis, flooding from elevated underground levels intersecting the land surface. The severity and frequency of flooding is influenced by extreme rainfall, high temperatures causing fast snow melt, high temperatures causing ice breakup, antecedent high soil moisture, antecedent high river or lake levels, wind chills conditions that produce significant fragile ice, which is slush consisting of ice that form in water that is too turbulent to freeze over, climate change, bad land use practices, and steep slopes. Floods are one of the most devastating natural disasters. Understanding the drivers of floods is therefore critical for effective flood forecasting. Data analysis modeling can help in understanding the potential impacts of floods and in developing strategies. Let us explore the use of data analysis modeling for flood forecasting. Mission of Flood Forecasting Center is to provide strong science-based hydrologic forecasting, flood warning and hydrographic reporting at all levels of government, private sector and the public. The main tasks include giving direction to emergency response, facilitating optimum operation of water control works such as dams, diversions and floodways to flood damage reduction, conducting hydraulic analysis using state-of-the-art models for flood forecasting and flood damage reduction studies, and to assess impacts of infrastructure changes such as road and bridge replacements. Modeling dam operations for flood control and to ensure a sufficient supply of water in reservoirs and rivers and suitable lake levels for recreation and fish, promoting long-term flood damage reduction by ensuring that developments, subdivisions, permits and crown land sales adhere to provincial land use policies regarding the risk of flooding and erosion, operating a provincial hydro network of water level and stream flow gauges, and provides hydrometric data near in real time for multiple use, contributing hydroclimatic information for the design of water control structure. Typical flood products are precipitation maps, soil moisture maps, snow water equivalent maps, issuing timely flood alerts, watches, advisories, warnings, daily flood report summaries, week flow volume rates, level reports or some table summaries, daily, weekly ocean tides and wave actions, wind setup and wind alerts on major lakes. An important part of flood forecast system involves collecting pertinent data and information, both meteorological and hydrological. These data are typically analyzed by computer models that provide flood level and volume simulation that are used to inform the public and multiple stakeholders. The art and science of the challenges in flood forecasting. Occurrences of extreme hydroclimatic phenomena are complex and chaotic with random and deterministic components. Flood forecasting faces challenges of complex uncertainties from a variety of sources, such as the chaotic random nature of the atmosphere, land, ocean processes. The chaotic phenomena is often caused by incomplete knowledge of the system, including initial conditions. Errors in the initial conditions can grow with time to make long-term predictions unreliable, even for a deterministic system, a phenomenon called the butterfly effect. Although the application of chaos theory remains mainly in the realm of research, literature is replete with discussion of the subject. With the emergence of powerful computers, significant advances in the area of chaos theory are being made. Forecasting weather and floods is both a science and an art. The capacity to combine scientific analysis with informed instincts and sound judgment. The science lies in the ability to understand how different atmospheric and hydrologic systems interact to generate floods, and the ability to apply and or customize the right forecasting tools to accurately mimic the evolution of a given event. The art of forecasting mostly develops with experience and includes the ability to make timely and reliable decisions and to choose the best forecasting tool in a given situation. Hydrologic systems are generally complex, and physical laws that describe natural hydrologic phenomena are difficult to formulate. Thus, a recourse to hydrologic models is made, whereby hydrologic systems are represented by a set of simplified mathematical equations. A hydrologic or flood model has three basic components: input, for example, rainfall; processing system within the study area, for example, watershed; and the output, for example, river flow or level. Forecasting model can be classified as stochastic, deterministic, lumped, distributed, or event based. A forecasting system can be either one or the combination of more than one. There are many different tools across the globe that are applied by flood forecasting agencies, ranging from simple regression techniques to more physically based models. Some are freely available, for example, HEC, HMS, HEC-RAS, SWAT, etc. Others are proprietary, for example, MikeFlood, MikeShed, etc. Flood forecasting requires a good understanding of spatial characteristics of input processes such as precipitation, land use, and soil patterns. These spatial patterns are now being incorporated into flood forecasting models based on GIS. In this manner, GIS provides opportunity to both describe and visualize spatial behavior of flood generating processes. Further, the model outputs such as flow rates and water levels can be visualized as they vary in both space and time. It is vital to provide margins of uncertainties in flood forecasting in order to help emergency managers and other stakeholders prepare for the worst scenarios of flooding. These uncertainties can be estimated through incorporating statistical technique in flood models. A collaborative approach to flood forecasting would involve bringing together a variety of stakeholders, including local, state, and federal agencies, emergency managers, academic researchers and experts, and the members of the public. This approach would involve exchanging information, coordinating resources, and developing strategies to better prepare for and respond to future flood events. During a flood event, coordinated participation is critical. That would involve incorporating the voices and experiences of those most affected by floods into the forecasting process. This could include engaging stakeholders in the forecasting process, collecting data from affected communities, and working with community partners to develop tailored solutions. This approach would acknowledge the importance of local knowledge and prioritize community-driven solutions to flooding. Into the future, real-time data become more readily available from automated earth-based sensors, for example, soil moisture probes, hydrometric and weather stations, and air-based platforms like drones, radars, satellites. Flood prediction models can be built to take advantage of such information by including data assimilation technology, among others. The technology can automatically ingest real-time data as they become available. Apart from the data assimilation capacity, adaptive models can be designed to use feedback mechanism where errors in previous predictions are utilized to improve future forecasts. In addition, model parameters can also be allowed to change with time during the simulation period, a process particularly attractive when parameters are very sensitive to environmental variabilities. This way, uncertainties can be accounted for. In particular, environmental prediction models with automated adaptive features can be very useful in flood forecasting, reservoir operations, irrigation scheduling, and other environmental predictive systems. The future of flood forecasting will be improved by generating automated state-of-the-art technologies, including global Earth observation platforms, numerical weather models, and flood forecasting models by the use of large memory and high supercomputers. Flood warning and alert systems can be more effective when a participatory approach is put in place. A process where the stakeholders, public, are properly engaged in critical processes during pre-flood preparations, planning, the flood event occurrence, and post-flood programs. As well, during developmental phases of scientific tools, modeling and forecasting, PA can offer insight into flood products' consumer needs. At the minimum, a well-designed PA model consists of synergies, protocols, and feedbacks to ensure cost effectiveness and maximum flood damage reduction emanating from the system's implementation. Climate variabilities and change can trigger changes in hydrologic cycle, land use, land cover patterns, leading to potential impacts on magnitudes and flow timing. Climatic processes constitute a major part of hydrologic cycle. Hence, the study of climatic variabilities and changes and their potential impacts on hydrologic systems cannot be overemphasized. Analysis techniques should adequately anticipate possible impacts of climatic variability and change on flood generating processes. That means a flood forecasting tool based on historical data may not be effective with time and needs to be adjusted with time. Traditionally, parameters derived from extreme hydrologic statistics were based on the assumption that the climate system would be time invariant. Such assumptions may not hold because of expected potential climate change due to global warming. So, floods are increasingly becoming a global threat. Flood forecasting needs collaborative efforts in sharing knowledge, developing effective forecast tools. Governments need to invest adequately to build flood forecasting platforms. Aquaclim Enviro Solutions looks forward to collaborate with matters related to flood forecasting. This is the end of Series 3 of 4-part series. Aquaclim Enviro Solutions thanks everyone who enjoyed this presentation. If you have any questions or clarification, feel free to write to us in the comment below. You can also drop your queries, comments, or suggestions on our website as well. You will find the link to the website in the description below. Stay tuned, we'll be coming back with our last series of 4-part series on climate and floods.